So, we will continue our previous thing. We were discussing the continuity of the functions. So, and we have defined a function is continuous if the limit of the function f z when z approaches to z naught exist and coincide with the functional value of this. Now, in case if the limit does not exist, all the function limit exists, but it differs from the functional value, then the function will not be continuous. All the function itself is not defined at the point z naught, then also it will be a discontinuous function. So, let us take an example 1 for the continuity first. Before starting for the analytic function, is this function is f z defined by this real part of z square divided by mod z square when z is not equal to 0 and 0 if z is 0. Is this function continuous at z is equal to 0? So, first thing is the function is well defined at the 0. Now, you have to calculate the limit of this function f z when z approaches to 0. Okay. So, if we look the function f z, the f z is basically coming to be real part of z square divided by mod z square. That is the same as z square is x plus I y whole square, and that is the same as x square minus y square plus 2 I times x y. So, real part of this will be x square minus y square over z square is x square plus y square. So, normally when we have a function in the rational forms and if the degree of the numerator and denominator is the same, then in that case the limit may not exist. Okay. So, that gives a clue. It means the limit of this function may not exist. So, function may not be continuous. So, let us start with the various path. So, I just choose the path y is equal to m x. Okay. So, as z tends to 0, it means x will go to 0, y will go to 0. So, we say x will tends to 0, y will tends to 0. So, when you substitute y equal to m x, it is reduced to a function of x, and we say limit of this function f z when z tends to 0 is the same as the limit of this function x tends to 0, x square minus m square x square divided by x square plus m square x square. So, that is 1 minus m square over 1 plus m square. Now, it depends on m, depends on m. So, limit varies as the m changes, y equal to m x changes, the corresponding limit changes. So, limit does not exist. Therefore, it is not continuous at 0. Okay. So, this will be the then we go for this differentiability of the function. This is the example of a continuous function, continuous function continue. Okay. So, examples of the now definition of the differentiability of the function. So, differentiability of a function f z. Let f z be a single valued. Now, we will always look the single valued functions. Okay. Let f z be a single valued function defined over a domain D. The function f z is said to be differentiable at a point z equal to z naught if the limit of this function, limit of this ratio f z minus f z naught divided by z minus z naught at z approach to z naught exist, that is whatever the path you choose, limit should exist, or with epsilon delta definition limit must exist, satisfy the epsilon delta definition, then this limit exists. We denote this as f prime z naught and we say the function has a derivative at a point z naught equal to this value. Okay? That is what. So, when we say the limit exist, all this can also be written like this, substitute z minus z naught is delta z, then the same thing we can put it as f z naught plus delta z minus f z naught over delta z and limit delta z goes to 0. This is the same as the limit derivative of the function. So, either we use this formula or maybe this expression, both will give the same. Okay. Now, obviously, if the function is differentiable, it must be continuous. Every differentiable function is a continuous function. Every differentiable function is continuous. The reason is this, because start with f z, this we can write it as f z minus f z naught divided by z minus z naught into z minus z naught plus f of z naught. The same thing. Now, as z tends to z naught, from the 1 the limit exists. So, limit of this ratio f z minus f z naught over z minus z naught, this will come out to be f prime z naught exist and this will give the 0, then plus f z naught. So, what you get? Limit of f z when z tends to z naught is f z naught. So, this implies that limit f z when z tends to z naught is f z naught. So, is it not a continuity condition? So, f is continuous. F is continuous at z naught. So, every differentiable function which is differentiable, it has to be continuous there at that point. If a function is continuous at every point in the domain, then we say it is continuous throughout the domain, and similarly the differentiability also. Okay. But the converse is not true. The converse need not be true. That is, if a function f z is continuous at a point z is equal to z naught, then it may or may not be differentiable. It may or may not be differentiable at a point z equal to z naught. That is, continuity does not imply always differentiability, but differentiability always implies the continuity. For example, if we look the function f z at z bar, then the limit of this function f z when z tends to say 0, z tends to 0, this limit is what? Limit of this x tends to 0, y tends to 0, z bar means x minus I y. So, it is 0. Okay. And in fact, if I apply the epsilon delta definition, same thing will go. So, for epsilon and delta definition also, we can say mod of z bar minus 0 can be made less than epsilon, provided mod of z is less than delta. Mod z means mod x is less tending to 0, x by tending to 0. So, this will go to 0. So, it is continuous. at z equal to 0. But if I look the differentiability, then f z minus f 0 divided by z minus 0 limit z tends to 0. What is this? Limit z tends to 0, f z is z bar, f 0 is 0 and y is z. And this is the same as limit x tends to 0, y tends to 0, x minus I y over x plus I y. Now, again you choose the different path. So, if you take the path 1, when x tends to 0 first, y tends to 0 later on, then this equation 2, then 2 will give limit z tends to 0 of z bar by z of this edge. When x is tending to 0, then what happens? This I by I gets cancelled and the value will be minus 1. Case taken, if y tends to 0 first, later on x tends to 0, then 2 will give the limit by z 0. So, it is x over x, the limit will be 1. So, limit varies when the path changes. Therefore, limit does not exist. Limit of 2 expression does not exist. So, it is not differentiable. So, f z equal to z bar is not differentiable at z equal to 0. Okay? That is what. So, the conversion need not be true always. Now, there are functions which are differentiable only at a single point and nowhere else. There are the functions which is differentiable everywhere throughout the complex plane, and there are the functions which are differentiable only inside certain domains and outside it is not there. So, let us categorize these. So, suppose I take this function f z is equal to say mod z square. Now, we claim that this function is differentiable at z equal to 0 and nowhere else. Nowhere else, because what is the limit of this? F z minus f z naught over z minus z naught, limit at z tends to z naught. If I conclude this, it is mod z square minus z naught square over z minus z naught, limit z tends to z naught. Or this is the same as limit delta z tends to 0, z naught plus delta z whole square minus mod z naught square divided by delta z. Is it not? But this will be equal to z naught plus delta z into conjugate of this mod z square z z bar minus z naught conjugate divided by delta z and limit delta z tends to 0. So, if we simplify it, z naught get cancelled and what you are getting is that z naught into delta bar z plus z naught bar delta z divided by delta z, and then another term which you are getting is delta z bar. Limit of this as delta z goes to 0. So, if delta goes to 0, delta bar z will go to 0. So, it is no problem, and here it can be written as z naught. This is what? Delta x minus I delta y. This will be z naught bar delta x plus I delta y over delta x plus I delta y, limit delta x tends to 0, delta y tends to 0, and this is 0 part. So, there is no problem. Now, again the limit, when you choose the limit, suppose delta x tends to 0 first and then delta y goes to 0. So, when delta x goes to 0 first, this is 0, this is 0. Okay. delta x is 0. So, what you are getting is here from, say delta x is 0 is z naught minus I delta y, z naught plus I delta y, and then divide by I delta y. So, delta y gets cancelled. So, what you are getting here, z naught with minus sign, I delta y is out, plus z naught plus this, that is all. This is the value of the limit. So, limit will be, this is the limit, this will be the limit, will be this. Is it not? By I delta y gets cancelled from here and minus z naught, or here this z naught. And when delta y goes to 0 first, and then delta x goes to 0, then the limit will come out to be, now delta y goes to 0 first. So, this part is 0, delta x out. So, limit will be z naught plus z naught bar. Now, here you are getting z naught plus z, here you are getting minus z naught plus z naught. These two differs. Therefore, limit does not exist. Delta z tends to 0. F of z means this mod z square does not exist, or sorry, z tends to, it does not exist. So, it is not differentiable at z naught, but if I take z naught to be 0, what happens? If I take z naught to be 0, z naught bar is also 0. So, limit exists, and in fact, with the help of the epsilon delta definition, you can prove that this limit exists. So, for z different from 0, limit the function f z which is mod z square is not differentiable. However, if z is equal to 0, then the function f z is differentiable, because this limit will exist. Whatever the path you choose, it will get the same thing. Epsilon delta definition will help you in getting the result. So, that I am leaving to you. Okay. So, this part, it means this is the only function, this is the function which is differentiable only at single point 0 and nowhere else, and rest all it is not different. But if we look the function, another function f z which is say e to the power z or z square or maybe z cube and so on, these are the functions sin z, cosine z, these are the functions which are differentiable everywhere in the complex plane. And in fact, the derivative will come e to the power z, 2i z, cosine z and so on so forth, like this. Okay. But there are the functions which are differentiable only inside the disk and nowhere else also, that also we can get it. Okay. Like 1 over 1 minus z, it does not, it is not defined beyond z equal to 1. Okay. So, this function is analytic or research only inside it, outside on the boundary it has a singular point. So, we are not going for this. Okay. So, this different type of the thing functions you can get which are differentiable at single point, nowhere else, and also in entire plane. Okay. We now come to our analytic functions. A function f z of a complex variable z is said to be analytic at a point z naught if it is not only differentiable at the point z naught, but also at every point in some neighborhood of z naught. What is the meaning of this? Suppose we say a function f is given and z naught is given. A function f is said to be analytic at this z naught if function is differentiable at z naught and there exists a neighborhood around that point, however small radius delta may be, such that at each point of this neighborhood function is also differentiable. So, when the function is analytic, then differentiability of the function at that point is not only necessary. What is necessary is that it should also behave properly, it should be differentiable around the point z naught also. That is why. So, there is difference between differentiability and analyticity. When we say the function is differentiable at a point z naught, we are not bothering much whether the function is differentiable at other point or not, simply continuity is important. But when we go for the analyticity of the function at a point z naught, then we do care the differentiability of the function in the surrounding point of z naught, that is in some neighborhood of z naught the function must also be differentiable at each point apart including the point z naught itself. Okay. So, this is the. So, for example, just now we have seen f z equal to mod z square. Now, this function is differentiable at the point z equal to 0 and nowhere else. So, it cannot be a analytic. So, it is not analytic at the point z is 0. However, if we look the function f z equal to e to the power z or sin z. Now, these are the functions which are differentiable throughout the complex plane. So, whatever the point you choose and whatever the neighborhood you choose around that point, at every point the function remains differentiable. So, it will be a analytic function throughout, okay, analytic functions. The functions which are analytic or everywhere in the complex plane is said to be an entire function. The function which are the functions which are analytic everywhere in the complex plane. Complex plane C are known as entire functions. Entire functions. Okay. Now, analytic functions are also known as holomorphic function or known as holomorphic functions. So, this is a new terminology which people use it, holomorphic function or analytic function. Okay. Now, as we have seen that functions, there are the functions which are differentiable, some functions which are differentiable, but not analytic, some functions which are differentiable only at some point and nowhere else or differentiable at every point. Similarly, analyticity also there. So, when we go for the concept of these analytic functions or to test the given function is analytic, what we need is that the derivative of the function must exist at the point z naught and in the surrounding of the z naught. But to test it those at those points which are infinite in number is not a easy task. So, what we do, we develop some conditions which are known as the necessary or sufficient conditions for testing the given function to be differentiable or to be analytic, and that will lead to the concept of the CRC equations. Okay. So, let us see first the conditions and then CR's equation. So, let us say CR's equation. These are known as the Cauchy-Riemann equations. Cauchy-Riemann equation. Cauchy-Riemann equations. In fact, it is given by Cauchy and Riemann, and the equations are in the form of the partial derivatives of a function u which satisfies certain condition. So, we will discuss what is the Cauchy. So, this Cauchy-Riemann equation comes out when we go for the differentiability of the function, the necessary condition for the differentiability of the function, all analyticity of the function. So, let us see the result. Theorem, just I am saying the result of theorem, the necessary and sufficient conditions for function to be analytic. Necessary and sufficient condition for a function to be analytic. Okay. So, first is necessary part. What this necessary? Suppose the function f, suppose the function f z is continuous, which is u x y plus I v x y is continuous in some neighborhood of the point z x plus I y, some neighborhood of the point z x plus I y, and is differentiable at the point z, at z, same point. Then what are the necessary conditions says? Then the first order partial derivatives of u, which is u x y, partial derivative of u, which is a function of x y, and v, which is also a function of x y, first order partial derivative of u and v exist and satisfy the equation del u over del x equal to del v over del y, del u over del y equal to minus del v over del x. Let it be 1. At the point z. So, what is this result says? If a function is differentiable at the point z, then it must, its real and imaginary part must satisfy this equation. Now, this equation is known as the CR's equations. This is known as the CR's equation. CR's equations. Okay. Del u over del. Now, similarly, if a function, hence you can derive, because if it is differentiable, then analyticity for the same analytic condition also, because if the function is analytic, it has to be differentiable. So, these are the necessary condition for the differentiability. So, it will be the necessary condition for analyticity of the function also. So, hence if f z is analytic, in a domain D, then the partial derivatives, then del u over del x, del u over del y, del v over del x, then partial derivatives, partial derivatives, del u over del x, del v over del y, del v over del x, del v over del y exist and satisfy Searle's equation, Cauchy-Riemann equations. Cauchy-Riemann equations. Okay, that is del u over del x is del v over del y, and del u over del y is minus del v over del x. Okay. So, this is conditions for. See the proof of this result first, and then we go for the sufficient later. Okay. Now, what is given is the function is differentiable. This is given function is differentiable. So, it means the derivative f prime z exists. So, limit of f z minus f z not etc. f z plus delta z minus f z over delta z exists. So, since the function f z is differentiable, at a point z, so the limit of this function f z plus delta z minus f of z divided by delta z at delta z tends to 0 exists, and the value we write as f prime z. Okay. This will be the. Now, f z we are taking to be the u plus I v. This is our f z. This is our f z u plus I v. So, if I use this thing z plus delta z is x delta x plus delta y. So, z is x plus I y, delta z is delta x plus I delta y. So, f of z is x u x y plus I times v x y, and then f of z plus delta z, what will be this value is u x plus delta x y plus delta y, okay, plus I times v x plus delta x comma y plus delta y, just in a similar way. So, now let us substitute it. So, this equation is set to, so put it in 2, f prime z, which is limit delta z tends to 0 means delta s goes to 0, delta y goes to 0. F of z plus delta z means it will be the same as u x plus delta x y plus delta y I times v x plus delta x y plus delta y minus f z, that is u x comma y minus I times v x comma y divide by delta x plus I delta y. Let it be third. Okay. Now, case 1 or path 1, because this limit exists, this exists, this is given. So, whatever the path you choose, the limit comes out to be the same. So, I choose the first path as delta x tends to 0 first and delta y tends to 0 later on. Then as soon as you put delta x to be 0, then what happens is this x u x by plus delta y minus u x by I delta y. So, we are getting from here is limit f prime z is equal to limit delta y tends to 0 u x by plus delta y x delta x 0 by minus u x by this term, these two terms I am choosing, then divide by I delta y, and then from here is we get limit delta y tends to 0, I is out common. So, I times v x comma y plus delta y minus b x y minus v x y, okay, v x y divide by I delta y. Now, let us see, this delta y is tending to 0, there is a change in the second coordinate y is changing to y plus delta y, there is no change in the x coordinate. So, it means you are taking the partial difference, this is the partial increment in u keeping x as constant, and when this partial increment is divided by delta y. So, this is the ratio of the these changes delta partial difference in y divided by delta y. So, limit delta y give the partial derivative of u with respect to y. So, you are getting this is 1 by I del u over del y. Similarly, when you go for this I get cancelled, here there is a partial increment in v divided by delta v. So, it will give the value del v over del y. Is it okay? Del v over. Now, this is say 4. Okay. Now, second path you choose, second path, suppose delta y goes to 0 first and delta x goes to 0 later on, then in that case we get f prime z equal to limit delta x tends to 0 u x plus delta x comma by minus u x y divided by delta x plus I v x plus delta x y minus v x y divided by delta x. So, again when you take the limit of this, then you are getting this is again the partial increment in x. So, it will give the del u over del x, and this will give I times del v over del x. Fifth. Now, 4 and 5th gives the same value, because the derivative exists, So, limit exists, therefore, compare it. So, compare the real and to real, imaginary to imaginary. So, what you get is that del u over del x is equal to del v over del y, real to real, and imaginary to imaginary. So, minus I will come here. So, del u over del y equal to minus del v over del x, and these are called the CR's equations. So, if the function is differentiable at the point, then at that particular point the CR's equation must satisfy it. Similarly, if the function is analytic at the point z naught, then the CR's equation must satisfy at this point. So, these are the necessary conditions which we see. It means, if a function f whose real and imaginary part does not satisfy the CR's equation, then the function will not be analytic or will not be differentiable, is it not? Because these are the necessary conditions, these are not sufficient. I am not saying it is a sufficient condition. So, basically we say these conditions are not sufficient or not sufficient, means CR's equations are satisfying, but the function is not a analytic function at that point or not differentiable at that point. The CR's equation, this condition are not sufficient means that for a function f for which the CR's equation are satisfying at the point, but the function is not differentiable at that point, then obviously this will not be a sufficient. For example, let us see the function f z, which is x cube 1 plus I minus y cube 1 minus I divided by x square plus y square when z is not equal to 0 and equal to 0 if z is 0. Okay. So, suppose I consider this, then what we claim is the function u and v of this function satisfy the CR's equation, but the function is not differentiable here. So, we claim that the real and imaginary part u and v of this function f z, this function f z, real and imaginary part of this function f z satisfy CR's equations at the point 0 0, but the function f z is not differentiable there. This we have claimed. So, if we prove this claim, then obviously these conditions CR's satisfying the CR's equation is not good enough to say the function is differentiable. Okay. So, let us see why. What is the function u? The function f z is the function f z is x cube 1 plus I minus y cube 1 minus I over x square y square, is it not, when z is not equal to 0. So, this function we can write like this, x cube minus y cube over x square y square plus I times of x cube plus y cube over x square plus y square. So, our u x y becomes x cube minus y cube x square y square, while the v x y is x cube plus y cube when x y is not equal to 0 0 and 0 when u is 0, v is 0 0 0. Now, we claim this function u and v satisfy the CR's equation at 0. It means the partial derivative of del u and v must satisfy that condition. So, what is the partial derivative of the? So, let us see what is the del u over del x at the point 0 0. But consider this. By definition, we are differentiating u partially with respect to x at 0. So, there will be change in x variable only. So, u x 0 minus u 0 0 divide by x and limit x tends to 0. This will be the del u over del x at the point 0 0. Now, u is this. So, when you take by 0 and then u becomes what, x, this is 0 by x. So, it 1. Okay. Similarly, if you go for this del u over del y at the point 0 0, then what we see here, this is the limit by tends to 0 u 0 y minus u 0 0 divided by y. Again, when you take x is 0, it is coming to be minus y divided by y 1. So, it is minus 1 and del u over del v over del x at the point 0 0. Similarly, you can prove, similarly you can verify that del v over del x at the point 0 0 comes out to be 1, while the del v over del y at the point 0 0 will also be 1. So, we are seeing that del u over del x is 1, del v over del x is 1, del u over del y is minus 1, del v over del y. So, del u over del x is del v over del y. So, we get del u over del x is del v over del y at the point 0 0, which is 1, and del u over del y is minus del v over del x at 0 0. So, CRs are satisfied, are satisfied. CR's equations are satisfied, but the function is not differentiable. But what is the derivative of the function? But limit of this z tends to 0, f of z minus f 0 over z minus 0. Now, this is nothing but what is our f? F is this function, is it not? Now, this function f z can be written as our x cube 1 plus I minus y cube 1 minus I divided by x square y square f 0 0 0 over x plus I y, and limit of this at z tends to 0. Okay. Now, this expression we can write like this. Can we say this is the same as limit 1 plus I x cube plus I y cube divided by x square plus y square and then x plus I y, is it not? Just you can manipulate it and get this result. So, that is not a big problem. Okay. Now, multiply by its conjugate, limit z tends to 0, multiply by conjugate. So, when you multiply by its conjugate, you are getting this limit z tends to 0 means x tends to 0, y tends to 0. Okay. Then or z y equal to m x also. So, 1 plus I x cube plus I y cube x minus I y divided by x square plus y square whole square, because this is x minus I x plus x square plus y square. So, it gives us square. Now, substitute y is equal to m x and let x tends to 0. Then what happens? When you substitute y equal to m x here, then x is out, x is cancelling, and what you are getting, the limit comes out to be, limit will come out to be 1 plus I 1 plus I 1 minus I divided by 1 plus I equal to m. So, it is x m. So, here is m cube, this is m, this is m cube, m cube. Okay, I will write again, sorry, I will write this. So, take this, substitute m. So, what you are getting is limit y equal to m x means limit x tends to 0, 1 plus I x cube plus I m cube x cube x minus I m x divided by x square m square x square as x tends to 0. So, this x square x goes out, x to the whole gets cancelled, and we get this value is 1 plus I 1 plus I m cube 1 minus I m divided by 1 plus m square whole square. So, this limit depends on m. Therefore, it will not exist. So, function f z is not differentiable at z equal to 0, although CR's equations are satisfied, CR's equations are satisfied. So, this shows that CR's equations are not sufficient conditions, are not enough to show, are not sufficient to show the function f z is differentiable or analytic at the point z naught, z equal to z naught also. Clear? So, this. So, what we get. Okay. Now, if we look the converse part of it, converse means the non satisfying the CR's equation will give the condition. So, remark, if a function f, if real and imaginary part of a function f z, which is real imaginary part of the function f z, which is u plus I v, does not satisfy CR's equation, then CR's equation at some point, CR's equation at z equal to z naught, then the function f z will not be analytic at the point, at that point, that is z equal to z naught, because CR's equation is the necessary condition for a function to be analytic or to be differentiable. For example, if we look the function f z, which we have already seen that mod z square, this function is not analytic at the point 0, is it not? Is not analytic at the 0, because the function is not differentiable at the point around the 0. The reason is, when you take the f z, what is this? Is nothing but the x square plus y square. So, our u becomes x square plus y square, v becomes 0. So, when you take the del u over del x, it is 2 x, del u over del y, it is 2 y, while the del v over del x is 0, del v over del y is 0. So, except when x and y are 0, the conditions are not satisfying. So, when z is different from 0, z is different from 0, either x will be non-zero or y will be non-zero. So, all maybe both may be non-zero. So, if it not 0, then CR's equations are not satisfied. So, therefore, the function f z, which is mod z square, is not analytic at z equal to 0. Okay? That is all. CR's equation are satisfying at 0, but that does not mean the function is differentiable, because that is not a sufficient condition unless you prove that these partial derivatives are also continuous. That we will take up next time, that what are the sufficient conditions, what restriction, what extra condition you can put it on the partial derivatives, so that while satisfying the CR's equation will give the guarantee the function is analytic at that point. Thank you very much.